In this talk, I'm going to introduce my joint work with my former PhD student, De-Jun Feng. We would like to consider an iterated function system in which situation it will satisfy the weak separation condition. Actually, the main result was included in Chin's thesis. Okay. Now, I would like to introduce the main problem that we are in consideration. Suppose Q is a given number strictly greater than 1, and capital D finite digits require that A1 equal to 0. Okay. Now we consider the iterated function system with the ratio 1 over Q and with the translation digits in capital D. Okay. Now we would like to consider the so weak separation condition. We say this IFS satisfy the third weak separation condition if there exists a constant C such that for any integer n and any nth iteration of the IFS, then the maps in the nth iteration of this family of maps either they are equal or there is a uniform distance greater than C times Q negative n. Remember that Q is the 1 over Q is the ratio of phi I. Okay, I would like to draw one picture. So actually, this definition was due to Casino and Zim and the guy. Okay. So suppose this is an interval. It's a large interval. And phi I will map this interval into itself. Suppose the other one is also the endpoint of the attractor. Okay. So after the nth iteration, so each of these intervals of length Q to the negative n. Okay. So this says either the map are the same or the distance between them is greater or equal to a constant C times Q to the negative n. So Q to the negative n is just the length of each interval. Okay. So that means the distance should be relatively very large if they are not equal. So our plan is to classify all the pairs Q and D so that phi will satisfy the weak separation condition. And also we have an additional assumption that we would like to ask the attractor of this phi is an interval. Because if we don't add this assumption, you know that every IFS satisfy open set condition also satisfy weak separation condition. That would be too many. So we needed to add another assumption. So in the picture, that means the intervals should be touched together. There is no gap. If that holds, then the attractor is an interval. There is some equivalent formulation of this problem. Okay, here we give another formulation. So given this digital set D and the number Q. So we consider there's a finite sum of AI Q to the i's power, where each coefficients AI are required to be included in D. Okay. Now this is a discrete set, so we can put all the elements together and rank them in an increasing order. We call this set XDQ a De-Jun set in R plus, means the positive x-axis, if there exist two positive constant C1 and C2, such that the gap between each two digits xn plus 1 minus xn is less than or equal to C2, but greater or equal to C1. Okay. So the previous problem is equivalent to classify all such pairs such that XDQ is a De-Jun set in R plus. Yeah, just by definition, so it's quite easy to see. So De-Jun set, so just equivalent to phi satisfy the weak separation condition together. The attractor is the interval. Okay, so that's the problem. Actually, this problem is closely related to a very old problem. Now we consider a special digits set from 0 to m. Also consider the distance set between XDQ and XDQ, which is equal to the summation of epsilon I Q to the i's power, where the coefficients is taken from the set 0 plus minus 1 plus minus m. Okay. So the question is, can we find all Q greater than 1 such that this difference set is dense in the real line? Actually, this question was first clearly stated in a paper by Zorbert in 1973. In that paper, he proved that this difference set is dense in R if and only if that XDQ is not a De-Jun set in 0 infinity. Okay, so that means in this special case, there's a question A is also equivalent to the previous problem. And I would like to mention that this question is also related to a project of Edwards, Joule, and Komornik in the 90s. Now, again, consider this special digits set from 0 to m, and consider this XDQ. So here, I simply write them as XMQ. So this is all the values of polynomial at the value Q with the coefficients 0, 1, up to m. So this is the elements in XMQ in the increasing order. And Edwards, Joule, Komornik define two numbers. I simply call them little l and big L. Little L just the limit in of the gap between xn plus 1 minus xn, and big L is the limit suit. Edwards, Joule, and Komornik ask in which case little l is equal to 0 and the big L is equal to 0. So from the definition, it's rather easy to see that XMQ is a Denon set if and only if both little l and big L are finite and strictly positive. But that's also just by definition. Okay. There is some simple fact. For instance, the big L is less than infinity if and only if that Q is less than or equal to m plus 1. So that's just a very simple argument. And Edwards and Komonic noticed one important property. They noticed that if a big LQ is equal to 0, then the number 1 will allow a universal Q expansion. Q expansion was introduced by Renyi himself in the last 50s. So here, one can allow one Q expansion with a sequence epsilon I, the coefficient sequence epsilon I in 0, 1, m. But this sequence can contain all possible finite sequence of digits. So any word of, over this alphabet will appear in this sequence. So that's the case when big L is equal to 0. Yeah, I think this is one of the main reasons that Edwards drew Komonic tell about this question. Now, let's turn to little l. Also, it's well known that little l is strictly greater than 0 in two cases. One case is that when Q is a Peso number, then little l is always greater than 0. And the other case is when Q is large enough, when Q greater or equal to m plus 1, also little l greater than 0. Now, I would like to introduce the definition of the Peso number. I'll recall that a Peso number is an algebraic integer strictly greater than 1, and all of its conjugates has a modulus strictly less than 1. For instance, consider this a golden number, square root of 5 plus 1 over 2. This is a Peso number. Why? Because it has only one conjugate. This is 1 minus square root of 5 over 2, which is less than 1 in modulus. Actually, there are countably and infinitely many Peso numbers on the real line. And moreover, the set of all Peso numbers is a closed set. Here, I would like to give a brief proof of the fact that if Q is a Peso number, then little l is strictly greater than 0. Okay, let's see. Suppose Q is a Peso number, and we can let Q1, Qd to be all the algebraic conjugate of Q. Well, so since Q is a Peso number, so the modulus of this Q1 to QD are strictly less than 1. So if we use rho to denote this maximum of the modulus, then rho less than 1. Notice that the gap between xn plus 1 minus xn for each n is equal to pq for some polynomial p with the coefficients in the set 0 plus or minus 1 and plus or minus n. Okay, so we need to show that for any such a polynomial, if pq is not 0, then pq should strictly greater than a constant. Indeed, that's the case. Suppose p is such a polynomial and pq not equal to 0, then its pqj and the conjugate are also not equal to 0. So we make the product together. We know that this is a non-zero integer. So pq will greater or equal to 1 over pqj, make the product. And since qj less than 1, so you will get an upper bound for pqj, and then reciprocal, you will get a lower bound. Okay, so that's the proof. When q greater or equal to m plus 1, also one can easily to say that pq also greater or equal to some constant. Okay, now I would like to mention one problem by Edstro harmonic. Actually, they asked that since we already know that little l greater than 0 if q is piezo or q greater or equal to 1. And they want to know whether or not they are the only cases for which little l is greater than 0. This question was open for a long time. But before we give the answer, we would like to address its connection to the study of balloonic convolutions. Yesterday, Hao also gave a talk on balloonic convolutions, so I simply recall part of them. Recall that given Q, the balloonic convolution mu Q associated with Q is simply the self-similar measure associated with IFS x over Q and x over Q plus 1. Okay, and for there's a balloonic convolution, Edwards in 1939 proved that when Q is a piezo number, then mu Q is singular, because the Fourier transform of the balloonic convolution at the piezo number has no decay at infinity. And later on, Sanem proved that actually that's the only case when mu Q, the Fourier transform, does not decay. In 1995, Boris Sonomiak proved that for almost all Q in 1 and 2, mu Q is absolutely continuous. In recent years, there are significant progress in the study of the dimension as well as the absolute continuity of balloonic convolutions, mainly due to the works by Borkman, Smetin, and Badu. Okay. But the open question that whether or not piezo numbers are the only class of numbers for which mu Q is singular is still remain. So I call this a question the Adolph's problem. So the Adolph's problem has not been settled down. In 1993, Carson now, in one of his papers, he gave a new approach in the proof of a singularity of Bernoulli convolution associated with Python numbers. They actually proved that the L2 dimension of mu Q is also less than 1, which together with some other result, it implies that mu Q should be singular. Okay, in his paper, he called a number is F number if this difference set intersect a special interval is a finite set. Okay, so this is an equivalent definition for finite type condition. Yeah, some of the audience might know that concept. So this is equivalent to say, okay, the IFS satisfy finite type condition. So of course, it's easy to check that for each Python number, that Python number always a F number. So Carson now ask whether or not there is a F number which is not Python. You know, if this is the case, then one can give a new example of parameters for which the Bernoulli convolution is singular. Okay. Now, I would like to address the progress for the study of the problem of the Adolph's jaw and Comonic about little l MQ. So there are some previous results. In 1973, Dropper proved that if Q is not an algebraic number, it does not satisfy an algebraic equation with coefficients 0 plus or minus 1 plus or minus m, then little m Q is equal to 0. In 1996, Bilgold proved that if Q is not a Python number, then when m is large enough, then this LMQ should equal to 0. However, he didn't give any information on how large m should be. 2 years later, Adolphs and Comonic gave us such a bound, but his proof is completely different. So if m is not enough, you see, depends on Q, then little m is equal to 0. In 2011, Sidorov and Smomiak proved that if Q is not a prime number, then little m Q is also equal to 0. Here we call an algebraic integer a prime number if each of the conjugate of Q is strictly less than Q homogeneous. Yeah. So that's some previous result before 2013. Then the question was completely settled down due to 2 results. One is by the result of Akiyama and Comonic in 2013, and my result in 2016. So Akiyama and Comonic proved that if Q between 1 and n plus 1, then this different set has no finite accumulation points if and only if that Q is piezo. And what I proved is that this property actually is equivalent to little m Q is greater than 0. So finally, we say this greater than 0 if and only if Q is piezo. Yep. So if we consider the special digit set of d equal to 0, 1 up to m, then that xdq is a Deterministic set if and only if that q is a piezo number in 1 m plus 1. Okay. So also there's equivalent to say for a special IFS x over q plus ai, where ai runs over the integers from 0 to m. Okay, that satisfy the weak separation condition together with a attractive Beer interval is if and only if that q is a piezo number in 1 and m plus 1. There is one consequence of the result of Akiyama and Kormanik that every f number should be a piezo number. But this is not so nice because we hope to find new parameters for which Bernoulli convolution is singular, but we cannot directly use this way because each f number should be a piezo. Now, according to this result, we know that if we choose the special digit set capital D equal to 0, 1, m, then our previous problems have been well understood because we get necessary and sufficient condition for the system satisfy the weak separation condition and with attractive being an interval. Now, we would like to consider the general case. How about the digit set not equal to this special set? There is a simple observation. For a given d, if you multiply it by a constant c, then there is nothing changed. So xdq is Deterministic if and only if xcd is Deterministic. So due to this information, we can make some normalization. So now, starting from the beginning, we assume q greater than 1, d is a digital set such that a1 equal to 0. And we can multiply this digit set by a constant so that the largest digit am is equal to 1 minus q negative 1. Under this assumption, we know that the largest point in this attractor is 1. Okay, so we know that k is included in 0, 1 interval. So now our question is, can we find all the pairs QD such that phi satisfy weak separation condition and together with attractor should be equal to 0, 1. Okay, equivalently, xdq is a Denon set in 0 to infinity. Q equal to 0, 1, this requirement is simple. It's equivalent to the gap between two digits, consecutive digits is less than or equal to 1 over q. So this is simple. Okay. So from now on, we can simply assume this property holds. Okay. So given q and given d, suppose this property holds. Now, I would like to present our first result. The first result says if phi satisfies the weak separation condition, then Q should be a Perron number, and all AI should be contained in the rational field of a Q. So this is a generalization of the previous result of Sidorov and Solomon. So there's a post for war IFS. So the main idea of the proof is to build a suitable substitution using this finite type condition. You know, I forgot to mention that if you assume the attractor of the IFS phi is an interval, then it satisfies the weak separation condition if and only if it satisfies the finite type condition. Okay. So when we have a substitution and we need to prove, in some sense, that whether or not is the substitution matrix is a primary, and we indeed we can prove that. So this is a improvement of a previous result of mine. Okay. Also, this is a necessary condition. Now, another easy fact, if you assume Q is a Peso number and also assume AI in the field of Q, then it's very easy to say that phi satisfies the weak separation condition. The proof is same as in the special DC set when D take value 0, 1 to n. Okay. So similar to the question of Edward, Stewart, and Komonic, one may ask, in the general assumption of Q and D, do we always have this implication that when phi satisfies this weak separation condition, does it means Q should be Peso? We know this is the case when D take this special DC set. Okay, and our question is, it really depends on the cardinality of the DC set. If the DC set has a cardinality between 2 and 4, then Q is Peso. But when the cardinality of a D greater than or equal to 5, you can always find an example that Q and is not Peso, but Q is still satisfies the weak separation condition. Okay, so this depends on the cardinality. But this didn't give a full classification. Our next result gave some more information. So if you put some more assumption about the IFS, other than the weak separation condition, we can still say Q is Peso. The first assumption is that if there is a constant C such that CD is contained in the set of rational numbers, or in another way, CD is just a subset of integers, then Q should be Peso. And the second condition is or. So this is the algebraic condition. Also, we have a geometric assumption. If the IFS, the gap between each 2 points, AI plus 1 minus AI less than or equal to 1 over 2Q, then Q also should be piezo. So the second condition, no, there's two conditions are separate. So if one of them are satisfied, then Q should be piezo. Right? So I would like to mention something more about the second the second condition. To guarantee the attractor is an interval, we only need to require that AI plus 1 minus AI less than or equal to 1 over Q. But now we require the gap is less than or equal to 1 over 2Q. Okay, so I call this assumption is a heavy overlaps. If you assume that your IFS has a heavy overlaps and also satisfy this weak separation condition, then there is no other choice. Q should be piezo. I wanted to first give you some example. For instance, in the cardinality equal to 5 case, then there is a concrete example for which the IFS satisfies weak separation condition, and the ratio Q here is non-piezo and non-silent. Now, I can explain a little bit more about the last statement. Heavy overlaps plus weak separation condition implies Q is either piezo or silent. So this is not in your statement. We say, okay, Q is piezo, but here I just wanted to mention some idea to prove this middle result. Okay, so Q is not a piezo and silent. Okay, so now I mentioned this special condition. Let's go. So this condition means, okay, what? Means under the first iteration, suppose this is the first interval, then assume this is the middle part of this interval, then the first interval will intersect with him. It must cross the middle point. And this guy. Okay, something like that. So you have a heavy overlap. This overlaps just guarantee one issue. The issue is that, for instance, if I choose that interval, if you remove this one, the other intervals still cover the attractor 0, 1. So that one is no use. So this heavy overlap just guarantee that if you remove one map, that does not affect the attractor of the new IFS is still 0, 1. Okay. Of course, you cannot remove the first one. You need to remove the middle one. Okay. The first one, if you remove this one, cannot be covered by the others. Okay. So only this property. And this property, we can use it in a special way. So suppose Q is not non-piezo and non-silent. Then Q has an algebraic conjugate, which has a modulus strictly greater than 1 and strictly less than Q. then we can build, use the weak separation condition, we can build a conjugate IFS X over Q and plus AI beta. Okay, here AI beta is the algebraic conjugate of AI in the field of beta. Okay. So we built a new IFS. The original one is X over Q plus AI, but now we built a conjugate. Now, there's a special property will tell you some information that yeah, we from that property and use some special analysis, complex analysis. We will see that the attractor of the second one, the conjugate IFS, is also contained in R9. Okay. So the beta should be a real number. And moreover, due to this finite type condition, one can build a one-to-one map between the attractor of the original IFS and the attractor of the conjugate IFS. And this map is one, I would say this is, yeah, there is a continuous map. This map is continuous. And either one maps, so given any point on the symbolic space, if we net pi and pi prime to denote the coding map associated with these two IFS, then you will always maps pi x to pi prime x. This is non-trivial because you know many points has different codings, but this result says it does not matter. Okay, you can always build such a correspondence. And that geometric assumption 3 also implies that F should be monotone increasing. And this will give us some contradiction. So I will just mention 1 minute to mention the contradiction. So here we have the IFS original. Okay, so after the nth iteration, you get some. So I just put the gaps. So gap, 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 gap. So each gap is greater or equal to C times Q to the negative n, right? But now, since there is a one-to-one map, so this one you maps to a new IFS K prime. So K prime, you get something different. You still also get some gaps, but this gaps which has ratios beta to the negative n, greater or equal to times C. However, beta is strictly less than Q. So it's a reciprocal. Beta to the negative n is strictly greater than Q to the negative n. But this is the attractor. So that means that the length of a K prime should be infinity, because the total different such intervals is greater or equal to Q to the n. But then Q to the n times this guy's should tends to infinity the length. So this is a contradiction. Okay, I would stop here. Thank you very much.